Hi, I'm Yossi Paltiel, the head of the Institute of Applied Physics and Electrical Engineering. We are in charge of the electrical engineering program, having 600 students as undergraduate studies and about 100 students for applied physics for graduate studies, both master and PhD students. We are doing physics, chemistry, engineering, and we are quite versatile in our program, as you will see. We have 12 PI, we want to grow to 20, and about 2 aluminum PIs, which are still active. And welcome to the Institute, and thank you for joining in. Yossi Paltiel. I am the head of the Institute, the head of the Brode Lab, and most importantly, the head of the Quantum Nanoengineering Laboratory. In our lab, we are trying to take or understand biological meaning or try to see biological processes, see if there are quantum processes in those biological processes, and take them to build devices, quantum and nano devices. So we start with biology, basic question about quantum biology, understand those questions, and then do transport and electrical measurement, seeing why it is important for biology, going to application at the end. So I would like to give one small example of how things going. We started asking why nature is homochiral. Why in nature we have only one chirality in nature, why the symmetry is broken, and we found out that this answer relates to spin. Wherever we pass current through chiral molecules, only one electron spin will go through. So this was starting by a basic question in biology. We found a mechanism in physics, and we can understand why it's important for biology, because we reduce scattering, we preserve angular momentum. So that's why every time charges go through protein, we don't want the protein to be conductive, but we want the protein to be immune against external fluctuation. So this is, we want the biology to be stable, homeostasis, against changing external condition. So let's start with this biological process, why it is important for physics, because there we can use it in a very simple way to do spintronic devices. We can have very high spin polarization by very small coating of chiral molecules. Another thing is, if you have more than one spin going through those kind of layers, like in respiration in biology, or photosynthesis, where we need the ox to have the oxidation, where we need 2 electrons with the same spin because the oxide ground state is a triplet. Again, we can understand why it is important for biology to be chiral, because we want the surface to preserve spin and to have 2 entangled electrons going through. Why it is important, again, to energy, because whenever we split water, doing the same as photosynthesis or in biology, wherever we do that, we think we want the process to be very efficient with no side products. So this is why if we align the spin in chiral potential, we see those kind of things. But we can also use it for energy, because wherever we split water, the hydrogen is at singlet state, but the oxygen is in a triplet state, so we have a more efficient energetical process with no overpotential. So we started with a very basic questions about quantum biology, ending with application in physics for spintronics, and also having green energy, where we have few startup companies. We are combining together physics, biology, and chemistry, starting from basic scientific question, ending with application, and our group is very diverse. Some of the students are working on superconductors, or the basic questions. So for example, superconductors with chiral molecules. Others working on rather immediate application, like batteries or improving batteries and green energy.
My name is Yael. I'm a PhD student in Yossi Paltiel's lab in the Applied Physics Institute in the Hebrew University. In my research, I explore the idea of using organic molecules in magnetic memory devices. The organic molecules is an easy and abundant and cheap way to control the magnetism of the magnetic memory device. Using this microscope, I'm able to directly image the magnetic domains of the device, and I'm able to see the effects of the chiral molecules on the domains. The domains are the internal magnetism of the materials.
This is a lab where we do the basic spintronic devices, superconducting spintronic devices. We study the devices with chiral coating, where we add the triplet state to the superconductivity and the spintronics through chiral molecules to standard devices. We measure the devices going from a room temperature down to 300 millikelvin with a gradient magnets up to 9 Tesla.
I'm a PhD student at the Applied Physics Department, and I'm studying nuclear spin effects in biological systems. We have just recently published a paper in PNAS discovering new nuclear spin effects in biological systems, specifically water entrance into human cells. I'm also studying the interactions between spins inside of proteins to explore how they interact and how they affect the protein folding process and how they help with the protein structural stability. I'm also studying how the spin-spin interactions in proteins affect their folding process and their structural stability. So we were able to observe nuclear spin effects using 3 oxygen isotopes inside of water molecules, and we looked at human cells and how the water molecules enter the cell, and we were able to measure differences in the isotopic ratios indicating nuclear effects in the process of water entering the cells. We were also able to observe very distinctive differences in the water splitting process when we used different isotopes of the water, like we did with the cells. So all in all, both chemical and biological processes were affected by the nuclear spin inside of the process.
Hi, good morning to the evaluation committee. My name is Dan Marom, and I will be describing a little bit my activity and my work here at the Hebrew University at the Institute of Applied Physics. So I joined here around at 2005 following a PhD that I had acquired in the US at UC San Diego. Following that, I worked for 5 years at Bell Labs, Lucent Technologies at the time, where I worked on photonic devices, specifically with a focus on wavelength selective switches. In 2004, I actually got a position here, but I only joined eventually in 2005 and made the transition from the US here to Israel. And I was actually the first recruit of the then Applied Physics department, following a very long hiatus in hiring due to various reasons. At the time, the Hebrew University opened the engineering school called the Computer Science and Engineering School. As I mentioned, I was the first hire in the Applied Physics department, and I joined a small department at the time, the most junior faculty amongst a faculty which is much older. And following, I guess, my hiring, the department continued to hire and expand, and we've seen tremendous growth since that time. And I've had the privilege, of course, of starting my lab, which I'll describe a little bit later. But in addition, I've also chaired the department for 5 years, which were a bit tumultuous just because during that time we had left the School of Engineering due to some differences in the role of the Applied Physics department, and we at that time became an independent department within the Faculty of Science, and then our hiring had continued since, and now we have transformed from being a department into an institute, which I'm sure Yossi, the institute chair, has spoken at length about. So I joined again in 2005, and I opened my lab, which I call the Photonic Devices Group, or Photonics Devices Lab, which has an acronym PDL, if you know what that is. During that time, we had pursued various projects related to photonic devices, with particular emphasis, I guess, on devices that are relevant for optical communication, so optical fiber communications. And during that time, of course, besides training numerous PhD and master's students, we had focused on making devices, both what we call linear and nonlinear devices, making use of both free space and much more focused now on guided wave solutions. And we're using various platforms such as silicon nitride, and again, free space optics. We're also now using new tools available to us, such as three-dimensional printing at the nanoscale, which allows us to fabricate photonic structures which control light propagation, and again, by creating structures which are both nano or sub-wavelength and more macro or bulk optics, but again on a very small scale. And again, together with fiber optics, so we use conventional fibers in the past, and since I guess 2010, with the advent of space division multiplexing, we're using more and more specialty fibers. So these can be both multimode fibers as well as multi-core fibers. So we're using those platforms to realize, I guess, innovative devices that we think can be of use for future optical communication networks, also for data centers. And then we look at ways how we can efficiently switch, filter, manipulate light that's coming from these fibers in order to achieve required functionality. Some of the specialty fiber at our disposal, or one particular platform we're advancing, is a unique fiber that's been made for us at Corning, which is a rectangular core fiber. So this is a fiber idea that we had devised of having a core which is designed to be single mode in one dimension and multi-mode in the other dimension. And that has huge benefits as far as both propagation, but also in device integration. And we're doing various devices using that fiber in order to demonstrate the ability of using this fiber in what we call MIMO-less, or without incurring mode mixing in the whole transmission link. So again, we focus on devices, but I have to mention that we're not really a system lab, so we don't have the capability of doing high-speed testing, like generating and detecting high-speed communication signals. For that, we rely mostly on collaborations. So we have a lot of joint activities with both research labs around the world, as well as industrial companies. And we typically collaborate in various funding schemes that create collaborations, such as the European Union, European Commission programs. And for instance, we have currently two programs running. One is called FlexScale, the other is called Proteus 6G. Both of them focus on communications for the upcoming 6th generation of cellular networks and looking at the backbone requirements for transmitting all the information there. And we have devised novel ideas in order to, again, control the data flows and increase the capacity and availability. We also collaborate in national programs. So we have 3 such programs, one on silicon photonics, the other on quantum communication, and the last on VCSELs. And for example, in the VCSELs project, we're looking at efficiently multiplexing multiple VCSELs, large arrays, into a fiber in order to have efficient power delivery. We have, of course, other different projects. I've mentioned a little bit the nanoscribe, or the printer that we print at the nanoscale, and we specialize specifically on printing on an optical fiber tip. We've demonstrated various functionalities. I'll just mention maybe one here of a sensor, which is basically a ring resonator on a fiber tip that's been completely 3D printed, and it's printed on a dual core fiber, so we can send light from the distal end of the fiber and get the reflected light or the returning light through the other core, so we get a very clean signal, and we can sense what's occurring at the distal end of the fiber. So these kinds of projects are all what we call the linear activities. We also have some activities in nonlinear optics and nonlinear signal processing using parametric processes. This has been a little bit downplayed in the last few years, but still we have that capability of looking at nonlinear phenomena in specialty waveguides that we've worked on in the past. But currently, again, the focus is more on devices and silicon photonics. One particular topic that we're trying to merge is, again, this ability to 3D print structures in the nanoscribe printer and using that to facilitate efficient fiber coupling between fiber and chip. So we have an experimental lab, which I'll take you on a tour soon, and you'll see some activities taking place currently in the lab. We have a fully stocked lab, again, mostly devoted to test and measurement equipment in the telecom region. So we're focusing mostly around the 1550 band. Recently, we're expanding due to expanding interest in the wider communication band, which we call the SC+L, which roughly extends from 1460 to 1625 nanometers. So we have tunable lasers, wideband sources, optical spectrum analyzers, and optical vector analyzers, etc. And all the students work collaboratively on the various projects and demonstrate what we're trying to develop, and then assist in meeting the requirements of the optical communication field.
Good day, my name is Alexey Kukin. I am a researcher in the lab of Marom, and here is a setup for characterization of VCSELs that we use in the project for efficient power coupling from the VCSELs in the fiber. VCSELs placed on this position, and here we collect light from VCSELs by objective. It's going through the splitter and going to the camera and to the spectrum analyzer, so we can get characteristic of power distribution in the beam and spectral characteristic of the VCSELs.
Sheffer. I'm a master's student at Dan Marom's lab. My system is a free space optic system. We're trying to achieve a true time delay with components such as grating, optical light modulator, and LCOS. Using this true time delay, we are trying to achieve a phased array that will be used for various applications.
Hi, I'm David. I'm a master's degree student in the Dan Marom lab. This is my setup. I have a silicon photonics chip on a vacuum table. On the silicon chip, we have a high performance mode multiplexer. My main goal is to create a transmission system that includes a fiber array, a vacuum table with a chip. On the other side of the table, we have another fiber array and another chip with a demultiplexer this time. And in between, we're gonna have a multi-mode rectangular core fiber. This technique is called space division multiplexing.
I'm Yoav Dana, PhD student in Dan Marom's lab. So I'm working on space division multiplexers especially photonic lantern multiplexers. We are fabricating it in the nanoscribe 3D nano printer and make these micro scale multiplexers. So besides of designing and fabricating, I'm actually characterizing it here in the setup. So we have this setup of digital holography that can resolve the eigenmodes and the field and the complex field of the system. So this is how we characterize it. Recently we took one of our devices to Brode Labs in the United States to make system experiment with it, and this work should publish very soon.
My name is Uriel Levy. I am a professor here at the Applied Physics Institute of the Hebrew University, and also affiliated with the Center for Nanoscience and Nanotechnology, where I served as the head of the center for the last almost 10 years till last September. My research topic is nanophotonics in general, and this is the laboratory for nanophotonics. The laboratory consists, besides myself, also a team of nearly 20 people, mostly students, PhD and master, but also some postdocs and permanent staff. The research that we do here can be divided maybe into 3 pillars. The first is nanophotonics, mostly plasmonic and metasurfaces. The second one is integration on a chip, mostly we can use the term silicon photonics. And the third one is a topic that we have pioneered, which is hot vapor on a chip. So these are the 3 major pillars. Let me tell you a little bit what we do in each of these 3 pillars. So as for metasurfaces and plasmonic, metasurfaces are basically man-made surfaces with nanostructure texture which is coming on top of the surface. And this field actually exists for maybe easily 20 years, but the term metasurface is relatively new. I was dealing with things relative or related to metasurfaces already in my PhD and my postdoc. And when I came here in 2006, I looked more deeply into these topics. Specifically, we are working on metal lenses. Metal lenses are flat lenses that could replace, hopefully, bulky lenses. But they have also lots of disadvantages. For example, chromatic aberration of such metal lens is much higher compared to the bulky lens. So what can we do about it? This is a topic of research. First, we have to understand the influence of this chromatic aberration, and then we have to seek ways to correct for these aberrations, and that's what we do in this activity. But we also do other metasurfaces, including tunable metasurfaces, which means we tune the properties of the metasurfaces after the fact, after their fabrication. And the metasurface could be like metal lens, as I mentioned, but in general, these metasurfaces can control amplitude, phase, polarization, and spectral properties of light using a thin sheet of structure rather than a bulky element, but they can also enhance light vapor, light matter interaction via the manipulation of the photonic density of states. So these are the major 2 directions in metasurfaces. They could be made of dielectrics like silicon, amorphous silicon, silicon nitride, but they can also be made of metal, which give rise to a field of plasmonics. Both has pros and cons. That's the topic of the nanophotonic or the metasurfaces. The other one is silicon photonics. We are active in silicon photonics in integrated waveguides with active components such as modulators and photodetectors. So we have demonstrated perhaps the best modulator about 10 years ago with the best figure of merit, bringing together very low loss and high efficiency of modulation. So combining these 2 together, that was probably the first silicon modulator that was demonstrated in Israel at the time. And since then, we're still working on this topic. In parallel, we also work on photodetectors with the goal of having photodetection at wavelengths like shortwave infrared and telecom, but using CMOS technology. So of course, the problem is that silicon does not absorb light at, say, 1.5 micron wavelengths. So the question is how to achieve such an absorption and how to achieve photodetection even though silicon is not absorbing light. So we came up with a concept of plasmonic enhanced silicon photodetectors in the infrared, and based on that we have performed a series of works in guided mode configuration and also in free space, and that was also a background to establish a company by the name Tri-Eye that is now producing this silicon-based imager for the shortwave infrared for the automotive industry. The third pillar is hot vapor on a chip. The main player in this field is what we call the ACWG, the atomic cladded waveguide. It's a waveguide typically made of silicon nitride, which is surrounded from all directions by rubidium vapor, thermal vapor that is moving around. And then we probe the atom via the evanescent tail of the optical mode in, say, the silicon nitride waveguide. So everything that you have seen from large bulky vapor cell we can do on a chip. And now there's beautiful physics around it because there are broadening mechanisms which are more dominant in our system, like Doppler and transit time broadening. There are effects such as surface effect, Zeeman frequency shift, light shift, and other fundamental effects that are more prominent in the system on a chip. So beautiful playground for research, but also lots of applications in, say, frequency references, magnetometry, maybe in the future chip scale atomic clock, who knows. So these are the three major pillars that we are active in. You can see here a lab where we do our chip scale work and the hot vapor. You can see a system to couple light in a chip, a system to perform imaging. On my back, you can see these coils that control the magnetic field. So they can cancel the magnetic field of Earth, and they can apply vector magnetometry in all three axes.
Microscope, you can see a metasurface designed for structural color. Here in the screen you can see what the microscope sees. The metasurface is using our own silicon-rich nitride technology, and what you can see here that we designed many nanoarrays, and each nanoarray is designed to reflect a certain wavelength, and hence you can see here many different colors.
Here we are in the Silicon Photonic Lab. In the Silicon Photonic Lab, we actually make some measurement for CMOS photodetector on chip. And so this is the chip, as you can see. So the measurement will be performed on this chip. And for the measurement, we need an electrical side and also an optical side. So for the optic point of view, we have two fibers. As you can see over here, this is the two fibers. What Gloria just moving is the laser one, the entrance, and over here is the exit that is connected to a photodetector. So the light goes through the device thanks to the fibers. And we have also an electrical side. This is the electrical pad. And we're coming with some electrical probe to make some flow of, be careful, of current. And the electrical the electrical probe are connected to some SMU, search measure unit, which we will do the measurement.
Welcome to our ultra-fast laser lab. In our ultra-fast laser lab, we are using a commercial femtosecond laser, and also we are developing new types of ultra-fast laser in the infrared regime. The purpose of this ultra-fast laser lab is to investigate high field physics and to investigate ultra-fast phenomena. Here you can see titanium cipher oscillator, which feeds all the ultra-fast experiment down the road. This oscillator is a very broad oscillator, and it also feeds the ultra-fast infrared laser that we are developing here. We are doing a few experiments with this ultra-fast laser. Some of them are high harmonic generation. We are investigating resonance high harmonic generation and the underlying physics below this unique high harmonic generation phenomena. Unlike regular high harmonic generation, where we have a typical spectrum of odd harmonics with a plateau that we call the plateau region, and we don't have any structure of the atomic that we are using. We can use neon, we can use argon, we can use even molecular gas, and with all these gases we have the same structure of the harmonics without any signature of the structure of the atoms that we are using. In our case, we are using evaporation of some metallics, and in that case we can see one of the harmonics which is pronounced with respect to the neighboring atomic, and this is a signature that we have some resonance involving in this process. Very interesting, this resonance is lying above the ionization level, and therefore this is a signature of multi-electron excitation. And what we want to study here is the dynamic of the multi-electron interaction and how they involve in this resonance harmonic. Another thing that we are doing here, we're taking this very, very broad spectrum of the oscillator, and we want to use it to generate ultra-fast laser in the infrared, with the goal to extend the energies of high harmonics into the kilo-electron volt, and also to investigate harmonics in solids. So what we are doing here, we're taking the very broad spectrum of the oscillator, and we can mix the red part of the spectrum with the blue part and generate a seed in the infrared. So here you can see that we are mixing the red part and the blue part of the spectrum in a nonlinear crystal and generating the seed in the infrared at around 2.5 micrometer. And then we are pumping with this home-built thulium-yield laser a unique laser material called chromium zinc selenide. This chromium zinc selenide is a very new and unique lasing material. It can laser in a very, very broad spectrum, and we are seeding this infrared laser into this chromium zinc selenide gain medium. We have a multi-pass amplifier here, and we can amplify this few nanojoule seed up to 1 millijoule pulse, about 50 femtosecond pulse. With this very unique infrared laser, we are doing a few experiments. One experiment is to generate electron-induced recollision, but in energies that exceeding 1 kilo electron volt. And we can use this electron to tunnel it out from the atom, accelerating it in the laser field and recolliding it back with the atom. Because of the unique wavelengths that we are using here, we can have very high energies of this recolliding electron. We can return it with more than 2 kilo electron volt, and we can excite inner shell electron. This is a very, very unique experiment that only we are doing here, and we can show that we can excite electron from the inner core shell of neon, krypton, and so on. So it gives us a unique tool to investigate the dynamic, the very ultra-fast dynamic of inner shell electron. Another thing that we want to do with this laser is to generate harmonics in a semiconductor. This is a new field that now people start to investigate since 2011. They're very much the same that we are doing harmonic in gases. We can do harmonics in solids. But in solids we have more knobs to play with because we have the symmetries of the solids, and we have the different band gap of the solid and the band structure of the solid. So the physics is much more richer of the harmonic in solids than harmonic in gases.
Hi, my name is Nir Bar-Gill. I've been here at the Hebrew University as a joint appointment between applied physics and physics for 10 years now, since 2013. And my research is focused on quantum information, simulation, and sensing experimentally using the platform of atomic defects in solid structures. Specifically, our work has been focused on NV centers in diamond, but we've recently expanded also to other material systems and to other defects, including, for example, boron vacancies in HBN and some other interesting 2D materials. Our work is trying to combine both fundamental aspects of quantum science, quantum technology, and advancing fundamental questions into quantum thermodynamics, control of open quantum systems, going from simple, well understood and well controlled few or single quantum system platforms, all the way up to ensembles of interacting quantum spins, where we have interesting questions associated with many-body dynamics, control, and non-classical states. In terms of applications, we're looking at how we can use these systems and the control that we have over them to create interesting sensors and to apply such sensors for questions in other fields. For example, we've been using these NV centers in diamond as magnetic sensors for studying magnetic van der Waals materials, recently identified, and a lot of interesting open questions are still being studied in this context. And going all the way from these interesting condensed matter systems to questions in chemistry, trying to characterize radicals in small volumes, and even to biological samples and trying to see how we can use our systems to characterize and to learn new things about medical constraints. This is the lab, and as you can see, it's essentially an optics lab. So we're building optical microscopes that allow us to look into these defects in the solid material. These defects are optically active, and that allows us to both address them locally and study their quantum properties, but then also to build interesting optics-based sensors that we can use them for. So what you're seeing here are wide field optical microscopes that we build around our diamond NV center platform that allow us to read out the optical signature of these NVs, and it carries with it the magnetic information which we want to measure, for example, for our condensed matter experiments, where we're looking at the magnetic properties of van der Waals ferromagnets and other types of materials which we can look at in these newly built systems. one kind of side project that comes out of this, which is actually a project that we're running now in collaboration with ELTA, the radar company, is to try to build a high sensitivity, high frequency sensor that could be relevant for such radar applications that they're interested in. Interestingly, this type of setup, while mainly designed for that high sensitivity application, is actually also well suited for studying highly dense spin ensembles for which interesting many body quantum effects can appear, and that's also something that we're realizing in this setup. I'll just briefly mention that in addition to these, we also have regular confocal microscopes in our lab. We also have 2 cryogenic confocal microscopes that we use for measuring at low temperatures, both for applications and for fundamental quantum questions. And we're also building a super resolution STED-based microscope that would allow us to measure beyond the diffraction limit and look at interesting dynamics associated with magnetic materials, excitations, magnons, fermions, and so on.
Hello, my name is Ori Katz. I'm a professor at the Institute of Applied Physics at the Hebrew University in Jerusalem, and I'm the head of the Advanced Imaging Lab. In our lab, we study and develop advanced techniques, both computational and physical techniques, that can allow us to image and see through complex media and turbid samples. These techniques use optics and acoustics, light and sound, to see through complex samples. One very common and perhaps the most important example is the human body. So we would like to see through the human body to see, for example, malignant tissues or internal organs, but unfortunately we don't seem transparent. So optical techniques such as optical microscope that we have here that are very useful techniques in general to see the surface of samples, the surface of the human body, surface of samples in industry and also outside academia. These cannot be used to see inside complex samples, and the reason is that we are not transparent, but although we seem opaque, we are actually turbid. You know, light can penetrate deep into our body, and we can see a small example. So we have here a regular light source, and when I put it through my finger, even though we have lots of light in the room, and even through my palm, you can see that light goes through the body. Unfortunately, this light is blurry and scattered, and it seems to not contain a lot of information, and our research goes into trying to distill information from these scattered light patterns, and we can distill information with computational algorithms. We look at lots of correlations inside scattered light, and we can try to undo the scattering and try to resolve this riddle by physical means. For example, we have many sorts of lasers, pulsed lasers, and we can send pulses into our body and watch the reflections, and from the reflections at different times try to understand what's going inside our body. So beyond these biomedical applications that involve light, we have the same problem in ultrasound. So ultrasound is also a very useful technique to look deep inside the human body, but ultrasound works best to soft tissue. So you can see internal organs in your abdomen, but it would be difficult to almost impossible to see the brain. Imaging the brain with ultrasound is not possible because of our skull. Our skull behaves in a scattering manner to sound as our other tissue behave to light. And the underlying equations and the physical models are the same for these two problems. So we try to solve optical problems such as light penetrating into our body, acoustical problems, ultrasound penetrating deep into our body, and actually from the mathematical point of view, this is the same problem in any complex medium. So it could be not just biomedical problems or challenges, but also here in this room, you actually can hear me because sound travels from my mouth to the microphone. Actually, the microphone is here. But also this sound reverberates in the room. There are lots of reflections coming from the different walls. And if you have multiple sensors, for example, as in this microphone array, and you record all of these time domain signals, and you do the right computational analysis, you can find from correlations within these signals, even from just random noise, you can try and reconstruct back a very sharp image, in this case an acoustic image, of the room, of the speaker, of the walls in the room. And actually you can use sound reflected from walls to hear around the corner. And so in acoustics maybe it's more trivial, you can hear echoes in a room. But what is less maybe trivial but comes from the same mathematical understanding is that even light, you can do the same with light. You can look at a wall, for example the wall behind us here, this white wall. You can look at the light reflected from the wall and see an image of the photographer now looking at the wall and using the wall as a mirror. So this could be done in optics, sort of looking around corners from the physical or mathematical point of view, looking around the corner using light reflected, actually scattered from a wall, is the same as trying to look through tissue, trying to solve this problem, this scattering or diffusive problem. And so these are maybe more scientific or biomedical scenarios, but we have the same problem also in very mundane day-to-day situations. For example, the fact that you can see me now is just because between me and the lens there is nothing but homogeneous air. But if the medium between us is not homogeneous, such as tissue, or in practical situation, fog, if you have fog, although fog is transparent, it is made out of water, you could not see through fog just because of scattering. From the mathematical point of view, it's the same as complex tissue. And if you look, and this is a very interesting problem from the industrial point of view, for autonomous vehicles and so on. And even in even more mundane tasks, if between me and you, I'm sitting in a conference room, and there is a frosted glass window or frosted glass door between somebody in the meeting room and somebody outside the meeting room, it will be very difficult to see the person inside the meeting room or in the shower, just because of scattering in this frosted glass window. And I have one example here. So this is an example of a frosted glass window. It's actually completely transparent. You can see my hand, but it's scattering. So light, the rays or the waves do not continue in straight plane wave configuration. And this is why it's very problematic to see me through the medium. But actually this is a very, from the mathematical point of view, this is a very simple, much simpler problem than looking through tissue. It's thin, and therefore it's defined by a single phase mask, a single complex function. And we now definitely can undo the effects of thin layers such as this frosted glass medium. Although it looks a very complex problem, this is a much simpler problem than looking through fog. So we have this problem as well. And so in general, we study wave propagation through complex media, and our approaches are based on a deep physical understanding, mathematical formulation, and today computational tools. That's it. Let's see some experiments.
My name is Omri. I'm a PhD student at the lab of Professor Ori Katz. In my project, we are trying to image samples, such as biological samples, through various light scattering media, and we go about doing that by recording holographic images, which record the 3D 3D structure of the sample, and we then try to invert the scattering process done by the scattering media in order to reveal those complex hidden objects.
My name is Jeremy Boger Lombard. I've been a student, I did my master's and my PhD student in this lab of Ori Katz, really since the beginning of this lab. In these past years, I done 3 different projects, and what we try to do in this project is to see, it can be to see through scattering samples, so to see through our skin, to see through frosted glass, to see through fog, all these kind of problems, and also the problem of seeing around the corner, which can be interesting for military application and also for autonomous vehicles. So in one of these projects, what we did, we took images of light that is reflected from a wall, from a white wall, and we were able to retrieve information about objects that are hidden around this wall. And after that, we moved to acoustics, because if we work in audible frequencies that our ear can hear, so in these frequencies, the sound that is reflected from the wall is not scattered. So it's much more easy to work with these sound waves and then to construct and retrieve the position and the shape of an object which is hidden around the corner. And in the last project that I did together with the student Omri Chaim, so in this project we were able to image full scattering samples. So it can be frosted glass, it can be even onion skin, which was an interesting target for us, or really biological samples like our skin, or even mouse slices of the brain of a mouse.
Hi, I'm Evgeny Slobodkin, and I'm a PhD student at the Advanced Imaging Lab of Professor Ori Katz, where we use imaging to solve all kinds of problems. We can use imaging of scattered light to build an anti-laser, which is a device that perfectly absorbs lasers that come from different directions. For example, in this setup here, we use this transparent piece of glass, and we turn it to a perfect absorber of this complex red input laser. So this laser comes from different directions, and it easily passes the glass when it simply goes through it. But if we put a few lenses around it, and we put a few mirrors around it, and we perfectly align everything, then this seemingly transparent glass can be turned into a perfect absorber of this complex input laser. And a similar problem can be solved to image the brain using ultrasound through the skull, which is a very important problem for biomedical applications. And it can be used to retrieve information from scattered sound from walls and from pretty much anything. So it is a very, very general field and useful for many, many applications.
My name is Agranat. I'm a professor of applied physics at the Hebrew University of Jerusalem, professor emeritus, I may add. And I'm going to give you a 3-minute glimpse of my laboratory, the optoelectronic computing laboratory. At the present time, we are working on 2 distinct topics of research. One of them is bacterial chemical biosensors, and the other is an investigation and development of devices that are based on the electro-optic effect in the vicinity of the ferroelectric phase transition. The first topic, we use live genetically engineered bacteria and the sensing element in an optoelectronic circuit. As such, the challenge of this project is to combine a biological entity, the sensing bacteria, with a technological entity, the optoelectronic circuit, so that they operate in unison and produce the chemical sensing operation. In principle, this can be used for a multitude of different applications in different areas. We are now concentrating on developing a technology for detection of buried landmines and concealed explosive charges. And in fact, we were able, with the two configurations which we developed, and you will see them in the next slide, to actually detect real mines in real minefields. And we are taking it forward, and eventually it will become a viable technology. I should add that this is, of course, there are obvious military applications here, but it is also a humanitarian endeavor. Around the world, there are 110 million or so buried landmines left over for past wars and military conflicts, and it's a major problem because the area where these mines were buried cannot be used unless these mines are deactivated, and there are thousands of casualties every year. So the cost-effective technology to detect these mines is the first step to activate these minefields. The second topic of research, as I said, is an investigation of the electro-optic effect in the vicinity of the ferroelectric phase transition. Special feature of this effect in the vicinity of the ferroelectric phase transition is that in the ferroelectric crystal close to the phase transitions, there are ensembles of nanodipoles that are float around in the paraelectric matrix of the crystal, and they actually dominate the ferroelectric effect, the electro-optic effect. The electro-optic effect in this region, it becomes very strong and fast, and we can use it for applications that could not be dreamed of before we had control over this effect. We started the research by inventing the crystal in which it happens. It's the Keltian crystal, potassium lithium tantalate niobate, that invented in our lab. And we are growing it ourselves, and we are investigating it. We discovered many very, very special phenomena. I'll mention two. One of them is the manifestation of a very strong or a very high index of refraction of 50 that happens slightly below the ferroelectric phase transition, what we call giant refraction. And the other one is a demonstration of the replica theory, which was the subject matter of the Nobel Prize in Physics in 2021. And we were actually mentioned by the Swedish Royal Academy in the Nobel document when Giorgio Parisi received the prize 3 years ago.
Yuri Feldman from the Institute of Applied Physics. So in the field almost 50 years, wow, quite a lot. And published quite a lot of papers, patents, and already have something like 17 PhD students successfully defended their theses in the field of soft condensed matter. So which is quite important and very, very promising, I think, in future especially.
Cindy Galindo. I am a fourth-year PhD student at Professor Yuri Feldman's lab. In our lab, we focus on understanding the water's unique biomarker properties, and by this, we have to understand something, is that, for example, in our body, water constitutes the 70%, and it uniquely interacts with other components as proteins, enzymes, and ions. And understanding these interactions is very important in the development of our projects. One of the most important projects that we are currently working in our lab is trying to revolutionize the current diabetes management. So it is well known that people that suffer from diabetes have to undergo finger pricking to monitor their glucose concentrations. And there is a high necessity to develop a non-invasive method. And in 2016, in our lab, was made a very important discovery. It was found the microwave dielectric sensitivity to the variation of glucose concentrations in red blood cell suspensions. And specifically, it was found a sharp minimum, here you can see it, sharp minimum, at exactly the highest allowed glucose concentration in blood. These findings shed the light on the possibility to apply our method to develop a non-invasive alternative to finger pricking. And our current work on this project aims to fill the gap between in vitro experiments and in vivo scenarios. So we are trying to approach those real conditions, and by those findings we aim to set the basis to develop a more accurate and more user-friendly alternative to the finger pricking.
Currently, this is quite an unusual lab in the Institute of Applied Physics. We are not doing nanophotonics, we are not doing quantum computing, spintronics, and metamaterials. Here we are in the lab which is busy with biophysics, soft condensed matter physics. And our main feature that we are covering extremely wide frequency band from 10⁻⁶, can you imagine, 10⁻⁶. This is, we are calling this durational PhD, up to almost 100 gig. And we can extend it even up to 1 terahertz. So actually we are covering the frequency band almost 17, 18 orders of magnitude, which is actually allowed us to study the very fast mobility and very, very slow mobility in all systems, including biological, which is quite important. And one of the most interesting feature of biological materials is water. And this is our main goal, to study water and its properties and to understand if water can be a biomarker, universal biomarker, to develop the different methods of the diagnostic and the remote control of biological and physiological state.
My name is Amir Capua and I head the Spintronics Lab at the Hebrew University. We're part of the Institute of Applied Physics at the Faculty of Science. In our lab we are trying to develop new technology that is very relevant to electronics and the solid state physics and solid state industry or semiconductor industry. We're working on the technology of spintronics, where we try to bring into action the spin degree of freedom of the electron that passes in the circuit. Traditionally, the semiconductor industry has related or used only the charge degree of freedom of the electrons that pass in the circuit. And in our field, we try also to benefit from the spin degree of freedom of the electrons. Our lab consists basically, our work consists of two parts. The first part is related to fabricating our materials and our devices. That happens in the, a lot of the activity happens in the clean room. We grow our samples and thin layers or devices atom by atom. We have a unique, very versatile, extremely versatile industry grade material fabrication system that we use. So our students take their wafers, the silicon wafers, they go to the clean room, they grow their devices layer by layer, and then they come to the lab and they characterize the spintronic characteristics of their materials. And when I mean spintronic characteristics, when I say spintronic characteristics, I mean the spin currents that pass in their devices. So the next phase of our work is consists of the characterization of our devices, and that happens inside our lab. And we have a variety of techniques that allow us to do that, all developed by ourselves. And these consists of optical methods and all electrical techniques. Basically, in order to understand what our devices are doing, we need to characterize the dynamics or the spin dynamics. So we can do that in our lab using the optical methods that measure the spins on very short time scales, reaching nearly femtoseconds. And then using electrical techniques, we can characterize much slower dynamics that are usually more relevant for the realistic applications. Our lab consists of 10 electrical engineers. And we're always, or in most of our projects, we're looking for the applications that we can do with this very fascinating technology of spintronics. Over the last year, we've applied for quite a few patents in various fields of technology that include metrology, advanced sensing techniques, and novel materials for modern electronics. Finally, after we finish the characterization, then we want to understand the behavior of our device. So we complement our experimental work with advanced modeling of the dynamics and of the spin dynamics in our work, that describe our work. And so in addition to the practical applications that we are looking for, we are also eventually looking for a new fundamental science that we can do, or that we can develop our applications or use in our applications. This is how, for example, recently we have realized that there is a completely new interaction that has been overlooked, where an optical radiation interacts with magnetism, or more accurately, we've identified the role of the magnetic part of the optical electromagnetic radiation in the interaction between light and magnetism, or light and materials, which was so far thought to be completely negligible. I find our work in our lab very rewarding, and I enjoy every day of my work working with our very talented students. The work is very challenging and very rewarding and very exciting.
My name is Liron Stern. I'm from the Quantum Sensors Lab. It's a relatively recently established lab in the Hebrew University in the Applied Physics Institute. This lab specializes in quantum sensors, and specifically chip-scale quantum sensors. So we try to realize small sensors based on this atomic vapor, small vapor cells that you can see here. These have inside atoms of rubidium, especially, and they're in a hot vapor phase. With them, we do all kinds of interesting sensing experiments. For instance, we do magnetometry. Specifically, what you can see here is remote magnetometry. We're sensing magnetic fields from distances of about 10 meters and sensitivities of picotesla. We do atomic clocks. We have small atomic clocks also based on this quantum infrastructure. Our clocks are optical atomic clocks specifically, and reach stabilities of nanoseconds at time scales of, I say, a month or so. We also do something called Rydberg sensing, which is electric field sensing. So all kinds of different quantum sensing modalities, all of them which we're striving to make them as small as possible. And the reason we're trying to make things small is twofold. I would say first, it's for realizing these kind of quantum sensing modalities in smaller and smaller packages. You can imagine having these things inside your cell phone. Other interesting kind of approaches with these kind of cells and sensors is This becomes a little bit bizarre here. If I take the cell now and I put it next to my head, and the neuron inside my brain has some kind of small current. This current establishes a very small magnetic field. Magnetic field that is like a billion times or more than a billion times smaller than typical magnets. It's 10 to the minus 12 in order of magnitude. And this small magnetic field in the brain, we can read it with this small cell. Here you can see one of our chips that we built. This is basically an atomic beam. So what we want to do, we want to have the atoms directed like a beam of light, but instead of light, the atoms itself are directed. So we have the atomic reservoir here, and we have these kind of grating structures that force the atoms to be collimated into a beam in this area here. We make these in the wafer scale, as you see here. So we make many of these cells, and we even can make many small, tiny cells like this one here. Okay, so one interesting thing we do with these tiny cells that I mentioned before, we can make these cells, these millimeter scale and submillimeter scales at the wafer scale. So you can imagine you have thousands of these cells at the wafer scale. And one interesting thing we did with these cells, we took a cell as such and a few cells, and we remotely put them far away from our detecting head. And from a distance of approximately 10 meters, we asked the question, what is the magnetic field at the vicinity of this cell? And we take the laser, it reflects back to our head, and we get the information of the magnetic field at a distance of 10 meters, reaching sensitivities of picotesla at that distance. And then you can imagine doing other interesting things. This is like the first time people did remote quantum sensing with these kind of cells. You can do Rydberg sensings that I mentioned before. You can ask what's the electric field. You can perhaps do other types of quantum sensings, maybe even time in the future. So that's super exciting.
And I am a researcher in the Applied Physics department here at the Hebrew University. I joined this department 2 years ago, and I do theoretical research in the field of quantum computers. I would say my dream is to contribute to this field and make this dream of quantum computers become a reality. I think over the last 20 years, this field has made amazing progress. Like 20 years ago, we saw just the baby steps of the field where people were able to take a quantum system, like an atom, put it in a trap and manipulate it with some lasers, but really do the very basic things of initializing an atom in some state and maybe transferring the population to another state. Now, 20 years later, we are in the stage where we can take like 50 or hundreds, and soon we will have thousands of atoms, and we can perform actual calculations. So initialize the atoms in some state, but then perform, tens of logic gates and actually get a result. And I would say the reason why this has been made possible is the combination of theoretical research and applied research, and this is why I was personally drawn to this field. My passion is theoretical physics, so what I really liked in my studies is math and the elegance of the mathematical formulation of quantum mechanics. I thought it is amazing that a particle can be in a superposition state and can be entangled. All these fancy words really caught my imagination and my passion. But quantum science is an experimental field, and I think this is really why it's so exciting. That now, more than 100 years after quantum mechanics theory was established, now we're actually starting to see its tools. At the Hebrew University, I have 5 master's students, and they are helping me carry out my calculations and check if my ideas or their ideas are actually applicable and actually helpful. What we do as theoretical researchers is we use pen and pencil, but we also use computers. We're especially interested in using classical optimization tools to optimize and improve the performance of quantum machines. So we are in this interface of optimization, what you call quantum optimal control, and quantum mechanics, the fundamental theory.
Jonah Waissman. I'm a recent faculty hire here at the Institute of Applied Physics at Hebrew University. I did my undergrad at Cornell University in the States, and my master's and PhD was at Harvard University, with my research performed at the Weizmann Institute of Science, also here in Israel. My postdoc was with Philip Kim at Harvard University. And my scientific interests are focused on low-dimensional systems. So that includes atomically thin layers, materials like graphene, the 2D semiconductors like the transition metal dichalcogenides, and also one-dimensional and zero-dimensional systems. So that means systems like carbon nanotubes, nanowires, gate-defined quantum dots, and so on. But my particular niche in my work is trying to answer the question of what can we learn about thermal transport in these low-dimensional systems. And this turns out to be a very tricky experimental question, because historically, although thermal transport has a long and distinguished history in the history of solid-state science, in low dimensions it's very hard to do. And that's because historically it's done by taking a bulk crystal that one grows and gluing thermometers, which might be little pieces of wire, for instance, thermocouples or other thermometer types that one glues to a macroscopic crystal. You glue a heater, you glue a thermal bath, and you can measure in this way the thermal transport through a macroscopic crystal. So if we're talking about mesoscale, atomically thin systems with lateral dimensions of micrometers, we can't do this kind of gluing. The trick that I came up with, or the technique that I developed during my postdoc, is to use the low-dimensional systems themselves as thermometers, and in this case we use graphene. And so the idea is we have sheets of graphene that we connect with other materials, and we measure what we call non-local noise. We perform what we call in total graphene non-local noise thermometry. And the idea is to use the electronic fluctuations of graphene connected to other low-dimensional systems as an electronic thermometer. And this has many key advantages. That includes direct contact between the two-dimensional thermometer and the system under study with no, for instance, glues or anything like this. There is very low energy loss to phonons in the graphene. So we can excite electrons and measure electrons while losing very little to no energy to phonons, to the phononic environment in our graphene thermometers. And so this gives us also extremely high sensitivity because we're dealing with a two-dimensional electronic system in which the energy is generated and deposited as well. With this, we were able to demonstrate electronic thermal transport in two-dimensional systems like graphene itself, in one-dimensional systems like carbon nanotubes, and in zero-dimensional localized systems like disorder-induced Coulomb blockade. With this approach, we hope to now study many new systems of interest that have long been impossible to measure in terms of their thermal transport properties. And so this includes measuring the thermal Hall effect, the electronic thermal Hall effect in low-dimensional systems, things like spin-liquid systems, hydrodynamic systems where we can look for the effective interactions on thermal transport. And that's what we will be doing in my lab, which is now under construction and is hoped to be finished in the next few months. Thank you. Hi, welcome to our future lab. This is where we will have our dilution fridges. We'll have here a magnetic material-free zone with the height that you see required for these fridges, which will be suspended on frames. Further in the back, we'll have our sample preparation area, including everything necessary for the preparation of van der Waals materials and devices, and stacking and glove box environments and so on. Thank you.
My name is Shiloh. I came here about half a year ago from a postdoc in Germany. There I was researching how to apply lasers to accelerate electrons, and not just to accelerate them, but to accelerate them on a nanophotonic chip. the nanophotonic chip can be as small as a hair follicle. And this implies that we can actually take the large facilities that now exist to accelerate electrons, which could be kilometers long, like the SLAC accelerator in the United States, and compress them into centimeter size or even less. One of the interesting applications is, for example, in medicine, where we could take such an accelerator on a chip, place it on an endoscope, and in principle, potentially insert it into a patient's body and irradiate a tumor in a localized fashion, taking care of a small tumor just like that. The applications of accelerators on chip or in principle in a tabletop device is also very beneficial for researchers in any academic lab. If one could use high energy electrons in an academic lab and not go to, again, some large facility somewhere, perhaps we can advance research worldwide in a much easier sense. Such devices can be used not only in academia, but perhaps also in industry and in medical facilities. These can be perhaps taken on board vehicles or into any hospital, perhaps, to be used for irradiation or for medical therapy or for medical imaging. The good thing about using these is that, or using this idea, using this technology, is that you can easily fabricate it in any clean room, in any university. You can create perhaps a small product that can be sent and distributed by the thousands quite easily. Let me now tell you a little bit about the physics behind the nanophotonic accelerator. When you take electrons and photons, for example, with a laser pulse and an electron pulse, and you try to make them interact in free space, you'll notice that then the energy and momentum conservation cannot be met, at least in the linear regime. And for that, we use the nanostructures. The nanostructures act like a mediator. So you shoot the laser pulse onto the structure, and you get evanescent field, or near field, through which the electrons go through. Then they can interact, assuming that you have your structure contributing the exact momentum that's needed. And we do this with the nanostructures, which are in principle just diffraction gratings. Once electrons go through the structure, and this is, mind you, a 200 nanometer gap, then they can interact with the photons in order to either accelerate or manipulate the electrons themselves. In our case, and this is a milestone that we've published only a couple of years ago, we've shown for the first time that you can use this kind of nanophotonic structure with laser light to guide electrons inside the structure. And let me repeat, this is a 200 nanometer gap over several hundred microns, and we want to show that we can get electrons through the structure with maximum throughput. And this is what we've done. And that was nicely published in Nature and recognized worldwide. But there, what we actually showed was just guiding of electrons. The next step of actually guiding them, so keeping the electron current through the structure and accelerating, was also just published last year, 2023, also in Nature. And there we have shown that we can accelerate electrons with these kind of structures in a scalable manner. And that's a very important step, because other acceleration technologies which use laser light without nanostructures have this issue of being able to scale their structures or their acceleration to larger distances. And so they usually have only one or at most two acceleration stages. With our technology, we can, in principle, accelerate to any energy from 1 eV to few giga-electron volts. In principle. Of course, that might take a few more years. For these efforts, which I pursued together with the research group in Germany, I was awarded the Röntgen Prize, which is a prestigious prize awarded once a year for one person in Germany. And I'd like to say one more thing about nanophotonic accelerators. You don't only have to consider the applied science side of it. There's also the question of actual fundamental research into physics, and in particular the quantum effects between light and matter. And we've also published another paper on that, on the photo-induced electron, near-field electron microscopy effect, where you have the quantization of the electron wave packet using photons. And that was a very interesting route to follow, which is something that I intend to also follow with my group now. So let me conclude. I came here about 6 months ago, and my lab is still under construction, but the options, the opportunities, I would say, are endless, from fundamental research, light electron coupling, to applied research like nanophotonic accelerators, and perhaps one day to get to some kind of product in our lifetime that would help humanity.
Hello, my name is Ilya Goykhman. I'm a new recruitment of the Hebrew University. Actually, I'm coming back from my journey to Alma Mater, so my PhD is from the Institute of the Applied Physics. So I came back home. My research span integrated optoelectronics integration with the two-dimensional materials. I recently won the ERC grant on multi and hyperspectral photo detection. So what I do in my research is actually integrating two-dimensional material systems with the classical optoelectronics devices based on silicon and other semiconductor materials. In particular, I focus on silicon photonics and integration of 2D materials such as graphene and transition metal digital cogonites with the silicon photonics integrated devices. I develop multi and hyperspectral detectors based on silicon and hybrid two-dimensional materials. I also focus on quantum integrated photonics, developing single photon emitters and entangled photon sources based on two-dimensional materials, and also take advantage of the flexibility and strain capabilities of the two-dimensional materials and develop flexible and variable optoelectronic devices based on these material systems. My future lab is going to be 100 square micrometers. Actually consists of 4 bays. For characterization, I heavily use the excellent nanofabrication center for any devices that I'm going to fabricate, and also going to heavily use the Brode Center in the Institute for Ion Implantation. This is very relevant for my ERC project. Despite the fact that I've just started several months ago, I already have 2 PhD students and a lab engineer and more people coming, because the topic of my research is exciting, and many people want to join and participate in the group, and I hope it will be a huge success in the Hebrew University.
My name is Yehudit. I am the engineer in charge of the Brode Lab. We are here in the Brode Lab now, and I will start a process for writing a submicrometric 3D structure using the nanoscribe system. First, I'm preparing the substrate. This is the polymer. And now I'm opening the software, which will send the model that we created to the machine in order to print it. I need to choose the correct setup. One of the interesting things here is that we can see all the printing process by the camera that is attached to the equipment. It began printing. This is the laser that we can see. And in some minutes, we'll start to see the shape of the model that it's been printed now. So I'd like to talk about this lab. The Brode Lab is a complex of cleaning rooms, and it was established about 10 years ago, thanks to a generous donation from a Canadian family, the Brode family, led by Anna in memory of her husband Peter. So this lab is part of the Anna and Peter Brode Center for Advanced Quantum Materials. The initial purpose of this lab was fabricating miniature integrated systems, and this has been done since then by using the nanoscribe system, which is based on a 2-photon polymerization technique. Since then, many researchers and their students fabricated very complex submicrometric 3D structures in a variety of different applications. In these days, the lab is going through a significant expansion to house an ion implanter system. We're talking about a medium-range implanter fabricated by the French company IBS. The energy is 200 kilo-electron volts for single charged ions, and it enables a variety of different species to be implanted. I want to emphasize that it will be the only system here in Israel to provide full access for all academic research teams. And this is an important point because this was the reason for acquiring such an equipment. And there are several areas of interest, such as solid-state physics, quantum physics, nuclear physics, atomic physics, material properties, modification. So this equipment, it will be here in Israel, and we expect fully operational in the middle of this year, 2024. Besides the implanter, we're also preparing a 2D room for assembling 2D materials and van der Waals heterostructures. The 2D lab equipment will include a high-end optical microscope for inspection, a dry and a semi-dry transfer station, chemical hoods, and annealing furnaces. There are various applications that may benefit from this platform for developing integrated electro-optics, quantum photonics, multispectral detectors, and even wearable devices. So in conclusion, the Brode Center for Advanced Quantum Materials is a service supplying lab open to all research teams and for every person interested in the unique technologies offered here.